The variable of the week is going to be humidity, moisture. Everything we want to know about moisture. I think most of you are interested it's going to rain on you when you're outside, or it's going to be cloudy so you can't get a suntan. All of those things are related to the moisture in the atmosphere. So we're going to talk a little bit about that right now. See if we can learn a little bit more about moisture. So there's something called an atmospheric river. It gets its name because it transports a lot of water. You can see a picture of one here with the clouds coming across the Pacific Ocean. It literally begins over in the tropical South Pacific and moves all the way across the Pacific and then into the northwestern U.S. Atmospheric rivers occur all over the globe, so this is not an anomaly, just looking at this one. They tend to occur in our wintertime, but you can occur other times of the year as well. And they're a mechanism to transport water from one location to another. So when that hits, gets lots of rain. Think about it. All that water is coming across the Pacific. It's been picking up all the water all the way across. A lot of moisture there. So the actual amount of water in the atmosphere is relatively small. If you were to dump it all out, you would average about 1 inch. It's not much. However, it can get concentrated in some areas. If you'll notice this last week when Helene came in and the massive amount of flooding that took place in western North Carolina, eastern Tennessee, that area, water vapor can get very high concentrations in one area and dump a tremendous amount there. So let's look at the general picture. Now, how does the water get into the air? Evaporation, right? Evaporation from lakes, from oceans, from rivers, and plants. Plants put water in the air. Part of their development and all. So they send some water back into the air. All of that gets the water into the air. Well, if the water just stayed in one spot, it'd go up over the lake, come back down over the lake or over the river. But it doesn't. Air moves, so it pulls this water vapor along with it. So as it's moving it along, clouds might develop in some area, and when the clouds develop, precipitation occurs. So that precipitation might occur on the ocean. So all you've done is put the water vapor into the cloud, bring it right back down into the ocean. Keep the ocean nice and moist. However, some of that might occur over mountains, or might even occur as snow on the mountains. And what happens if it hits a slope? West Virginia is classic for this. I learned this one real fast when I worked there, is that you've got all of these, literally they were told to me, be hollers, and that's a good term as any, that flow through, are in all parts of West Virginia. So when the water hits the mountain slopes, what happens? It comes down quick. Gravity pulls it down. It goes into these hollers, creeks, streams that are there. I had relatives that lived right along some of these streams, and water would come up very quickly, up to almost into their house sometimes, when the major flooding of that little creek occurred. With that, you can get the landslides and all that as well. In some parts of West Virginia, you get that. Now, say I live in Charleston. Charleston's relatively flat in the main area of the city, right? So what happens there? How does that water get into the Kanawha River or the Elk River? What happens is the water sits there and it gets taken in by all the sewage, stormwater drainage systems that have been put in place by us humans to get the water out of there to keep the city from flooding. When the land is flat, water doesn't flow very well. When the land is paved over, water doesn't flow very well out of there unless you have mechanisms to get it out. Oh yeah, the land will absorb water, and eventually there's groundwater storage. So you can see this whole pattern of water moving And we need water for life, so we want this to happen. So what are the different phase changes? We've learned all these. Evaporation, condensation. Transpiration is just water coming out of the plants. Sublimation, deposition. Precipitation is part of all of this as well. So humidity describes the amount of water vapor in the air. It varies all the time. The other day it poured down rain here. A couple days before that it was relatively dry. So one day it was fairly humid, one day it was not. And guess what? We have lots of mechanisms to measure humidity. Vapor pressure. So water vapor is a gas, so it exerts a pressure. Good enough. There we have a measure of it. Mixing ratio. Specific humidity. Relative humidity. Dew point. Precipitable water. So we're going to talk about it. Vapor pressure. Simplest one. The atmosphere has water vapor in it. The more water vapor in a location, the more moist the air is. Mixing ratio. All right, so this is a little more confusing, but not terrible. Think about if I pulled all the water vapor out of one mass of air. We'll say 1 meter by 1 meter. And I weighed that water vapor. Now, the remaining dry air, I weigh it. The ratio of water vapor to the remaining dry air is mixing ratio. That's all it is. Specific humidity, slightly different because I include the water vapor. In other words, it's the original mass of the air over the mass of water vapor. It's the only difference between the two. They're close, but they're not the same. Absolute humidity is the mass of water vapor, period. All right. When saturation occurs, in other words, that little part of air can no longer hold any more moisture, any more water vapor that comes in there has got to go back out. Just can't hold it. So it goes back out as probably a liquid. So when you do that, it's saturated. The air is totally saturated. That's how you get the rainfall. How you get fog, the air becomes saturated. So when you see clouds, the air is saturated in that area. All right, so the warmer the air is, the more water vapor it can hold. So in the wintertime, you don't hold a lot of water. Look at this table to the right here. And you'll notice millibars. So down here, 0 degrees Celsius, right around freezing, 6 millibars. Not much, really. However, 77 degrees here, Fahrenheit, 25 degrees Celsius, 5 times as much. We've raised the water temperature, the air temperature by 50 degrees or a little bit more, but we can hold 5 times the amount of water vapor. And if you go a little bit hotter, you really want to get a hot day, 95 degrees, I can hold another almost 100% more water vapor. So water vapor can be held a lot better the hotter the air is. That's why in wintertime, when we get rain, it tends to not be quite as heavy unless it's relatively mild. Summertime, however, it can pour down the rain because the air can hold so much more. All right, little thing. It's going to become the pressure of liquid compared to ice. All right, in a liquid, the molecules are moving a little bit more than they are in ice. Ice are kind of stuck there. They're not moving a whole lot. Liquid, they're moving a little bit more. That difference means that since they move a little more, it takes a little more air, a little more water to saturate it. So the saturation vapor pressure is going to be a little bit higher over liquid than it is over ice. It's going to play a role. Relative humidity, all that is is how much moisture you have compared to how much moisture the air can hold. If the relative humidity is 100%, you can't hold any more water. No more. If the relative humidity is 5%, it can hold a lot of water. So that's all that's saying. Simple enough. You've done it with a vapor pressure. You can do it with mixing ratio. Any way you want. All you're doing is calculating the relative humidity. How much more moisture would it take to saturate the air? What percentage of that air is saturated? So when somebody tells you in the morning that the relative humidity is 100%, think about it. They're saying it's probably foggy out or kind of yucky. All right, so since air temperature determines the amount of water vapor the air can hold, the air temperature gets hotter during the day. So if I don't change anything else of the amount of moisture in the air, the relative humidity will peak in the morning and go down in the afternoon. That's why fog dissipates. As the air warms, it can hold more of that moisture, the fog begins to go away. You see that in the mountain valleys? Warm air sometimes advects in. All of that. Dew point is just a measure of the temperature that if you cooled that air down to saturation, where the dew would begin to form. Literally, that is what it's saying. That would be the dew point. So, if I have a certain amount of moisture in the air and it's 50 degrees out, and if I cool that air down, and we'll say that, oh, it reaches saturation because I have a decent amount of moisture in the air at 45 degrees. That's the dew point. And the closer the dew point is to the actual temperature, the more humid the air is. The quicker that air will saturate and become able to produce fog, rain, whatever. Notice the dew points in the wintertime, they're relatively cool. Air can't hold as much moisture. In the summertime, it's pretty humid. And we've talked about clouds form because temperature cools. Think about it. If I'm pushing an air parcel up in the atmosphere, as it's rising, it's cooling. So if I keep the same amount of moisture in that parcel, eventually it's probably going to reach a point where it's saturated. Not always. That's why you have beautiful sunshiny days sometimes. But a lot of times it's going to cool to where it's saturated. And when it becomes saturated, clouds are going to begin to form. Now we're going to talk a little bit about stability. All right. Last week, we learned in temperature, the other week in temperature, that as the air rises, it cools. It cools at the adiabatic lapse rate, 9.8 degrees Celsius per 1,000 meters. So if it cools at that rate, dry air, what happens if the air is warm with moisture? So let's take an example of that here. The air parcel is being pushed up. Now, the temperature is never dry adiabatic when you go up in an atmosphere. It's always going to be a little bit less than that. How close it is to dry adiabatic, that can make a difference, but some days it may only cool off at 7 degrees Celsius per 1,000 meter. Other days it might be all the way up to 9 degrees Celsius. Sometimes it might be 5 degrees Celsius. But as that air parcel is rising, it reaches a point where it has cooled to the amount of moisture in it is now saturated. Saturation means that we are condensing the air, right? Condensation releases heat. That air parcel is no longer cooling at 9.8 degrees Celsius. It's cooling around 6 degrees Celsius. So, depending on the air temperature around it and how it's changing, that air parcel all of a sudden may become warmer than the surrounding air. Well, warm air is less dense, right? So less dense means it's going to rise because it's going to try to find its density. If it's more dense, it's going to want to sink. That's why cold, dense air sinks. So that is stability. That is all it is. Think of a hot air balloon. Hot air balloon is always hotter than its surrounding air, so it's rising. Same thing is happening with a parcel of air. And that parcel of air, you choose the size. It could be 100 meters across, it could be 1,000 meters across, whatever you want to make it. But think about it. That air parcel's not changing, not mixing with the air around it. It's just going up. Maybe it's been pushed up by a mountain. As it's going up, temperature says, hey, I'm cold enough to finally saturate this air. Oh, well, now I'm not going to cool as fast as the air around me. Well, the air around me, we'll say, was cooling at the rate of 7 degrees Celsius. So up until now, as that air mountain has been pushing it up, that air, because it was cooling dry adiabatically, has been colder. It actually wanted to sink back down. All of a sudden, now that air is going to say, oh, the next 1,000 feet I rise, I'm going to be warmer than the surrounding air. What happens? I want to take off and shoot upwards faster. I'm going to be unstable. That's all we're talking about here. So, lifting processes that can cause air to rise are things like mountains, convection, fronts, warm and cold fronts. And when air rises to the point it reaches saturation, it's called the lifting condensation level. Kind of important. It's where clouds will begin. So if you knew where the lifting condensation level was when you got up in the morning and you had no clouds in the sky, but you knew the air was going to be going up that day, that would be the level that clouds form. If you were a pilot, that's kind of important to know. Rain showers, think about it. If I have winds coming from the east into West Virginia, they hit the mountains, they go up, lots and lots of rain on the east side of the mountains. What on the west side of the mountains? Oh, not as much. Some of that nice moisture that came from the Atlantic Ocean got taken out of that air, so there's not as much rain on the west side. That's all the rain shadow is. Converging winds bring lift. So if I can get winds to converge like happens in Florida or along a sea breeze, I'm going to lift it up. I'm going to cause rain. So let's take a peek at a couple little things here. All right, so this is today's weather map. Dew points are on the bottom left, and the dew points over here, 67, 79. That is really humid. 70, 79 out of here. Lots of moisture going up along this side of this front. Less back here. Really, dew points back in here, 36, much less. So you can see the difference in dew point advection. And remember, moisture advects, just like temperatures advect. And with that, I wanted to show this one image. This is precipitable water. If I dumped all the water out from a whole column of air, this is how much water would come out. We saw those high dew points down here, 79. Look at this. Right here, very high precipitable water, over 2 inches. So anything over, in the summertime, over an inch is relatively high. Now all of this area here is over an inch pretty much. However, if you go up in the wintertime, precipitable water, if it gets over 3/4 of an inch, it's getting pretty significant. And sometimes you do get that inch or inch and a quarter. So you've got to understand the air mass you're dealing with. You're dealing with a cold one or warm one. So when Helene came in, it pulled all this 2-inch plus moisture up into here, dumped the rain out, advected that, all that kind of moisture in. So that's why it was such tremendous rain. So looking at precipitable water can give you an idea of where some really good moisture is. You can notice there's actually a little dry area right in here right now. So there's less clouds, and it's still humid, but not as bad. So Hope you learned a little bit about moisture today. Let me know if you have any questions, and especially stability. Please, I know that can be complicated, so don't hesitate to ask.